Hello. My name is Muhammad Tadanigo Santusila from Informatics 48 International class. My hands are tired, but okay, I just finished this. I didn't print it out, so I had to write down the questions as well. I'm sorry, but I just finished exams, finals, and I'm just way too tired to just run, go 20 minutes to go to the printer. I'm just way too tired. My hands are dead now. So, uh, while my brain is still quote unquote fresh, I'll explain a bit if I can about this. Man, this took me a lot of digging on the internet to do. A lot and a lot of calculating. Dear God. Okay, alright, let's start with number one. It's not wasting your time. Yeah. Due to a storm, air traffic control instructs a pilot flying at an altitude of 4 miles to make a 90 degrees horizontal turn while climbing to 4.2 miles. Now, the path of the plane during the maneuver is modeled by this function right here. RT 10 cos 10 PT 10 three things. These are three separate things. 10 sin, 10 PT, and 4 plus 0.2 T. And this T, the value of T is bigger than 0, but it is less than 0.05. Now, where T is time in hours and all distances are in miles, I have to do two things. Now, A, find the speed of the plane during the maneuver, and B, compute the tangential and normal components of acceleration, AR and AN. Now, which one is 0 and why? Alright, first of all, we need to find the velocity vector. Now, the velocity vector is founded by doing this, which is taking the derivative of the position vector, which is RT, with respect to time t. d dt. Okay. This thing and then calculations. I don't think I need to explain the calculations, right? This is just boring, right? And then it's just pretty much used to waste time. But blah 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 vt, the derivative of that, so to respect to the t. So just ignore anything else that doesn't have a t, and then put focus on the t, and then you got boom 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 boom. Cool. Now to get the speed of the plane, you need to get the magnitude of vt, which is this square root of that plus that plus that, blah 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 blah. And then thanks to trigonometric identity, which is sin 2x plus cos 2x equals 1, these two are pretty much non-existent. And then we just got this and this left. Now roughly 10,000 p squared is roughly uh 98,969.04. So plus 0.04, so we now get 0.044, which is roughly 314.16 miles per hour. That is the speed of the plane. Now we need to look at AT. Which one is AT again? God damn it, I forgot. Alright, okay, yeah. Basically the constant speed of the plane. Okay, so AT is to figure out if whether or not the plane changes speed during its flight. So pretty much just do this, blah blah blah. I'm not gonna okay, I did this on a separate paper because I'm not gonna do two papers on one goddamn question. So I had to do this on another paper, and I got the result. It's 0 because this is 0, and 0 divided by this, whatever this is, I didn't count this, but 0 divided by whatever it is, it's obviously going to be 0. Okay, and then AN, which is pretty much the direction, to find out if it changes direction or not, which is this. And again, I had to use a separate paper because come on, man, really. Okay, so got the results, blah da 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 da, and we got 9,869.6. So what does that mean? Okay, so we got AT is 0. Since the question asked which one is 0 between AT and a, that's AT, right? Whatever, it's AT and AN. Since AT is 0, it means that the plane didn't change speed at all. But since AN is not 0, it means the plane changed direction. But not speed, because AN is 0. Okay, that's number 1. I have a headache. So apologies if I get things incorrectly, because too many numbers. I just finished finals. Okay, number 2. A car travels during the curve y equals 1 over 3 x cubic. Now, where both x and y are measured in miles, the maximum safe speed on a curved path is inversely proportional to the square root of the curvature at that point. Now, I have to do 2 things. A, if a car can safely travel at 30 miles per hour at the point 1.1 over 3, how fast can it safely travel at the point 3 over 2 and 9 over 8? And B, I need to interpret the geometric significance of curvature in terms of road safety. Thankfully, B is completely rhetorical and non-numerical, but A is numerical. So let's explain that in a bit. Now, first, what do we need to do? We need to find 2 derivatives, because the curvature formula, requires the second derivative and the first derivative. So the first derivative of y is x squared, second derivative 2x. Self-explanatory. This is electric. You get 1 over 3 times 3, which is 0.33 times 3, which is 1. So it's x squared normal now. Cool. And we apply formula at 2 points, which is first the point 1.3, 1.1 over 3, and second one is 3.3 over 2, 0.9 over 8. This, don't ask. I have to use a second. Not making another paper. I counted on another paper. Okay. I saw the question wrong. So this is the result. That's the result. Okay, cool. Now we need to get to the maximum safe speed at the 2 different points. Now for V, this is the formula, K over K root. And since was blah 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 wee. It's just counting, okay? I don't think I need to explain counting. I need to explain the formula, not the counting. Okay. Then with this, we got the results. Boop boop. Okay, so that, ladies and gentlemen, is the safe speed at 0.3 over 2 and 9 over 8 is around 56.25 miles per hour. Now, we can talk about B, which is the interpretation of the geometric significance of curvature in terms of road safety. Now, that sounds weird, but believe it or not, there's actually application of this particular formula, of this particular question. And that is pretty much used, and specifically in the context of road safety, we can think of a U-turn, or just a normal turn in general. If you don't have a driver's license, I do, by the way. I have a car's driving license, not just a motorcycle. I have a car's driving license. I drive a car, so I know just how goddamn significant it is to have a good curve in a turn. I don't know if that's the right word, but if you're driving a car, you can pretty much if you're a driver with a driver's license, you can pretty much judge whether or not this turn is safe or not to do. And as a road worker, I feel like you shouldn't make a turn that's not okay to do. So this matters a lot. If an inexperienced driver see a turn and doesn't pay attention to the curve and just, okay, there's a turn, I should just turn. But the curve is not safe because you didn't see this. Let's say the safe speed is probably like 10 miles per hour or 2 miles per hour because the curve is just that weird. It's just that dumb. So now an inexperienced driver saw the curve and like, whoa, okay, I'm just gonna turn here and not pay attention. I'm just gonna go 20 miles per hour on a safe speed of 2 miles per hour. An accident is bound to happen. So that's the importance of this particular formula, and that's the interpretation, my interpretation of it in road safety at the very least. Cool. Okay. 10 minutes have passed. Wow. I do love yapping indeed. Number 3. Thankfully, this is a calculus material that I like a little bit more than Silo 3, Silo 4, my goat. Okay, number 3, the temperature in Celsius, of course, the greatest, at a point xy on a metal plate is given by the function Txy equals to 400 exponent to the power of minus x squared plus y divided by 2, comma, x is greater or equal to 0 and y is greater or equal to 0. Now, we need to compute the gradient vector f and interpret its direction in the context of how heat flows. And b, find the unit direction vector from point 3.5 in which the temperature remains constant. What do we do? First, partial derivatives, one of my favorite subjects in the calculus. Yippee! Cool. First, we need to find dot t, the what's it called? To the respect of x? Whatever, to the respect of x. So this remains unchanged because it's, of course, exponent is going to be the exponent. This remains unchanged, but it moves. This does still get derivative, just not here, over here. If we multiply it, so this to the respect of x, y is void. Why am God, I literally said, sorry, I just like this particular material in calculus. Okay, so yeah, that, and then we need to find the gradient vector. Boop, boop, boop. This is the gradient vector. Cool. Sorry, I said before that I'm not going to explain the calculations because that's just going to be a waste of time. I'm just here to explain the formula. Okay, so it is asked, interpret its direction in the context of how heat flows. Okay, so if it's positive, if this particular thing is positive, in which it's not, but if it's positive, then its rate of increase in temperature is increasing, so it gets hotter. But if it's negative T, which is this, then its rate is decrease in temperature, so it gets colder. I hope you understand what I mean by that. And finally B, we need to find the unit direction vector from point 3.5 in which the temperature remains constant. Okay, so we need to find a coordinate or a vector in which the temperature remains constant. Okay, so we just put in, so okay, we have this formula already, and we just put in 3.5. Very simple. That's why I love this particular material in calculus. And it's just simple. X is 3 and y is 5, blah blah blah, blah blah blah, blue blue blue. And then we find a vector that's orthogonal to this, which is this, or 1.6. With that, we find the magnitude of 1 plus negative 6. So 1 squared plus negative 6 squared, which is pretty much just 6 squared, equals to the square root of 37. Then the unit vector, which is I forgot to put in, but it's pretty much what do I do with it? It's this. Can you work? Pen, please. Pen. Oh my God. Okay, here. Okay, it's pretty much this. So we just put in 1.6 and then divide it by this. Boop boop. Done. Okay, this is the unit direction vector at point 3.5. 3.5, not this point, but the vector at this point when the temperature is always gonna remain constant. Okay, cool. And then finally we have the last question. A little bit harder than number 3, but we ball. Alright, so a candle manufacturing company produces candles at 2 locations. The cost functions in dollars for producing x1 units at location 1 and x2 units, okay, that's not supposed to be x squared, it's supposed to be x2 units at location 2 are given by this. Location 1, x1, 0.02 x squared plus 4x plus 500. Whereas for location 2, it's 0.05 x squared plus 4x plus 275. Now each candle sells for $15 reduce, and the total profit is this function: 15 times x1 plus x2 minus location 1 production cost reduced by location 2's production cost. Now we need to do 2 things. Find the value of x1 and x2 that maximizes the profit, boop, boop, and interpret your result in terms of how many units each location should produce. Look at all those number-do's. Alright. So, how do you find the value of x1 and x2? First, we need to substitute the cost function to profit function. So pretty much just insert the cost function to the profit function. See, this is pretty much, yeah, it's pretty much the same. So we just compute. Okay, this remains the same. This is that over there, and this is this over here. We boop 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 count, blah blah blah, wee, and then we got, and then we have to find the partial derivative of x1 and x2. In this case, the partial derivative to respect of the x1, it's negative 0.04 x plus 11. For respect to x2, it's negative 0.1 x plus 11. Now we need to solve for x1 and x2, which is blah 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 blah, and then we got the result x1 equals 275, which is 11 divided by 0.04. It looks weird, but that's just how math works. And for x2, it's 11 divided by 0.1, which is 110. Nice. Now we need to verify maximum using the second derivative test. This is kind of hard. I had to look through the internet to find this particular formula, or did Mr. Putu teach this and I forgot? I don't know, but I had to use this formula. I don't really quite understand it well, but here goes me explaining. Okay, you gotta use the formula using second derivative. Oh, well, I get the second derivative. I just don't understand the test part. Okay, second derivative of x1 and x2, that's pretty much a derivative of x and y. This is 0.0, negative 0.04, and x2 twice, it's negative 0.1, and x1, x2, it's 0. And then we have to use the Hessian determinant, which to find d. And if you look closely, this kind of looks like extreme, because it is finding the extreme, but it's just in a weird, it just worded weirdly. And you don't need a table because you only need find one or two. You don't need a table for that, so whatever. Then with these 2D, bop bop, boom boom, we got result 0.04 is indeed bigger than 0. Now since, like I said, it's finding the extreme, isn't it? It is, because 0.04 is pretty much fxx, just in a weird font. And d bigger than 0. So because it's bigger than 0, it pretty much eliminates saddle points. Rip bozo. So it's between local minimum and maximum. But since, remember, local maximum is, it has to be negative, while local minimum has to be positive. And since this is fxx, it's negative, that means it's local maximus. That's pretty rare. Yeah, we usually only get minimum, but cool. And for this, we get x1 275 and x2 equals 110. What's the interpretation of this? This one is very simple, unlike the one before and besides the traffic safety one. Pretty much, x1, location 1, needs to produce exactly 275, no more, no less, to provide maximus profits. For location 2, they need to produce exactly 110 products to maximize profits. And no more, no less. Remember, this is on location 1 and this is on location 2. Any more, any less, then you don't get maximum profits. You make too much, production costs too much. Make too little, you don't get much to sell. This is the perfect amount to get the maximum value. And that was me. I am Muhammad Dario Negocian Susilo. I can't flip my camera, so sorry. I'm using my only hands, no face cam, because, well, I don't have a tablet, I don't have a drawing pen, and I am way too tired to go to the printer. So I apologize if there's any mistakes. This took me so long. Thank you so much for watching until the end. See you. I hope I didn't get cooked on calculus this semester.